Saxon Algebra 1, Lesson 84. We got a two-topicer today. And the first topic is we're going to learn how to multiply radicals. It's pretty easy and it's pretty fun. Let's just pretend that these radicals we want to multiply are called m and n. I know, they're letters. Why aren't they numbers? That's because when we're trying to establish a general rule in math, we go to letters to sort of substitute for any universal number, right? It just makes them kind of generic so that we can focus on the rule instead of the numbers. You know the story of the three little pigs? The three little pigs, I assume they were brothers. We don't really ever know that. But what happens is they go out and into the world and they each build themselves a house. One of straw, one of sticks, and one of bricks, I believe is the way the story goes. But unfortunately, they have an adversary named the Big Bad Wolf, and he comes and starts blowing down the houses from the flimsiest of materials, and he slowly works his way up to the strongest. As each little pig gets his house blown down, he runs off and joins one of his brothers in his sturdier house. So to me, the way to multiply radicals is to invoke the spirit of the three little pigs. And remember, they can share houses or they can separate into their own houses. I call these shapes pig houses because that's what they are in my mind. It makes it very, very, very straightforward and easy to remember. Let's try an example. Okay, we're multiplying 4 times the square root of 3 times 3 times the square root of 2. Okay, well, wait a minute. This doesn't look like this because this has numbers on the outside. These numbers on the outside are the big bad wolves trying to get in. The numbers on the inside are the little pink piggies, safe and warm inside. So when we multiply, wolf to wolf and pig to pig. That is the rule. I want it in your brain for the rest of your life. You will remember it like this. We multiply the wolves and we get 12. We multiply the pigs and we get 6, right? 4 times 3 is 12. 3 times 2 is 6. This is our final answer. Whoa, it's that easy. Wolf to wolf, pig to pig. Let's try another one. Okay, so let's multiply our wolves. 4 times 6 is 24. And then our pigs, 3 times 6 is 18. But now we have a new situation. We have a root, a pig, that can be reduced, right? We know this because if we take the prime factors of this, which I will do, this is 2 times 9. Whoops. I jumped ahead in my brain. 2 times 9. 9 can be broken down into 3 times 3. That means that this is equal to, we can rewrite this answer as 24 times the square root of 2 times 3 times 3, right? Because 18 can be broken down into those factors. Now we have another rule that I need to help you remember. Besides wolf to wolf and pig to pig, the other rule is 2 pigs on the inside of the house equals 1 pig on the outside. 2 pigs and later I'll show you mathematically why this is true. But for now, I just want you to remember the rule. Make sure you get this copied well into your notes. These rules are gonna stay with us for a long, long time. So what that means is these 2 3 pigs that match, they have to match obviously, can come out of the house, but there's only one of them on the outside, and we multiply him by the wolf that's already out there. Somehow coming out of the house, I mean, I could build my metaphor. The 2 pigs come together and they can fight the wolf. I don't know. They turn into a wolf. I don't know. But 2 pigs in the house equals 1 pig out of the house. We multiply. This becomes 72. And then inside the house, all we have left is 2. This is the simplified answer to our problem. Pretty cool, right? Notice up here, we could have said, well, wait, why didn't we simplify this answer? Well, this breaks down into 2 times 3. Again, in order to simplify what's in a radical, break it down into its prime factor so you can see. There are no pigs to take out because there's no pairs of pigs. So that's why this was the final answer here. And we didn't even talk about it. Here, when your brain gets used to this, you'll go, oh, look, this is 9 times something. 9 is a perfect square. It's a pair of 3s. Therefore, I know I can take them out. So we look for those perfect squares in our numbers, okay? And if you're not sure, you can just do a prime factor tree of the number inside the pig house, and you'll be able to figure it out. Okay, let's bump it up another notch. Hey, I got a new notebook. Remember last time I filled the notebook? It didn't have any orange books, so I went for pure, pristine white for Algebra 1. Sorry, I'm thrashing around. Here we are. Put myself back in camera. P.S. I forgot to do this last time. Look. This is the last lesson for week 22. And I want you to notice there are only 3 weeks of new lessons left before we get to the midterm. And then spring break. All right, so 3 more weeks of new lessons before we get to the final. Ooh, exciting. Okay, we're on our 3rd example. And how many are there? Let me check. Oh, we're doing 4 of these and then we're switching topics. What? Okay, 84.3. This time, it's not just a simple multiplication problem. This time we're doing distribution. Well, distribution is just 2 multiplication problems in one, right? We'll multiply this one and then this one. It works exactly the same. So here we go, wolf to wolf, 20, pig to pig, 6. We can see that's 3 times 2. We know those are the prime factors of 6. We know that doesn't give us any matching pigs. So that's done. Now we'll go this way. Wolf to wolf is 24. And we keep the plus sign in here just like normal. 24. Now look what happens. Maybe we don't notice that these match. And we go, oh, it's square root of 9. And then we go, wait, 9 is 3 times 3. So now I can take a pig out of the house and multiply it here. Okay, that's one way we could do this. And then that would be 20 square root of 6 plus 72. That's one way to get the answer. The other way, after we did the first one, 20 square root of 6, as we're multiplying it, we get to 24. We could see right away, oh, look, that's going to be 2 3s, so that's going to be 2 3 pigs in the house. I can take one out. You can just skip right over this step if your brain catches it. If your brain doesn't catch it, that's fine. You'll catch it later. But if you do notice right away, oh, look, that's going to give me 2 3 pigs in the house, and I can take one of them out right away, go ahead and do it. So then again, we get the same answer, 20 square root of 6 plus 72. Either way is fine. As you do more and more of these, your brain will tend toward this. You'll tend to catch it earlier. But it's okay if it doesn't. Don't worry about that. 84.4. This is the last of these problems. simplify. 4 square root of 2 all right, it's another distribution. The wolves are 12. The pigs, I'm going to pretend I don't notice that those are matching pigs, and I'll do square root of 4 plus, now this is only a wolf, so it's just the wolf to wolf, 20 square root of 2, beautiful. But then I notice, oh, this is a perfect square, isn't it? It's 2 times 2, make my little prime factor tree. You can do it in your head too. And so I'm going to take these 2 pigs out. There'll be 1 pig out of the house. 2 pigs in the house equals 1 pig out of the house. This now completely goes away, and I get 24 plus 20 times the square root of 2. That's my final answer. Yay! So my friends, that's how we multiply radicals. It's so cool, right? It's all about the 3 little pigs. All right. Are you ready? John's going to turn this already significant lesson into a monster beast by saying, hey, let's talk some more about functions. Okay. A function, as we have seen, is nothing much more than an equation. But if you want to get theoretical and fancy, functions are a mapping or a connection. A mapping, that's the word mathematicians love. Between inputs, which are called the domain, a function is a mapping or a connection between the inputs to exactly one member of the outputs. What in the name of heaven am I talking about? Let's take a really simple example that we've worked with in the past. Oh wait, pretend I didn't write that there yet. I don't want to add those words yet. We know that in something like this, you can take any numbers you want for x. Let's take 1. You do the work, and you get the answer. And you can pick any numbers you want. You just plug them in and do the math, right? Let's do 3. 3 plus 2 is 5, right? We've done this, and then we've graphed the pairs, right? What we're saying is you can look at this very same exercise and give each column a different name. These are the inputs. You can call them the domain if you want. These are the outputs. You can call this the range if you want. And this is the part that we call the function. It's like the equation. Okay? And what the whole idea of a function is about, that gets mathematicians so worked up, is that every time we take one of these inputs, let's say 1, every time you take 1 and plug it into this specific function, you will always get the same output. You're never going to plug 1 into this function and get 7. It's 1 plus 2. It's always going to be 3. And that's the mapping that they're talking about, that 1 and 3 are connected by this function. I mean, kind of, it's just fancy names for what we've already done, right? Remember this, sometimes we also call this the input, and there are more fancy names for this we'll learn. And this is the output. It's just another name for the same thing, right? So this relationship between 1 and 3, that they're always going to go together when we're looking at this function, it's obvious. We know that, but we're giving fancy words to it and making a big stressy deal out of it as if it was new. All right? And John draws this same scenario somewhat differently. He draws it with shapes, which I kind of appreciate. This side is the domain, and he's using a different function in his function machine. He says, instead of just x plus 2, mine was easier. He said, let's do x squared plus 5. He chooses these values for x. He puts an x right there, and then he writes function, just like I did. And then over here he writes y. This looks an awful lot like this, doesn't it? It's just slightly different shapes. And then he calculates the values. And he doesn't leave room to work, which annoys me, but that's okay. If we plug 2 into this, we'll get 2 squared, that's 4, plus 5 is 9. So 2 and 5 represent that mapping, that connection that we see. 4 squared is 16, plus 5 more is 21. 4 and 21 are a pair, we can say that they're images of each other. 2 is an image of 9, 9 is an image of 2. They go together. Okay, 7, 49, plus 5 more is 54. Okay, so this is John's example that he wants to show to us. And he makes the point that 2 will always connect to 9, and 4 will always connect to 21, and 7 will always connect to 54. Just like we found here, right? I could draw the same kind of arrows. These guys are always going to be connected, right? They're the mapping. Okay, so now what John's going to do is going to show us some pictures like this, and he's going to show us that just by looking at diagrams like this, we can tell if a number is a function or not. Remember that each input has to be connected to exactly one of the outputs, just like our arrows show here, right? Okay, so now what we're going to do is we're not going to look so much at the function part of it. We're just going to look at the relationship of inputs to outputs, the relationship of domain to range, same difference. And we're going to look and see if this rule has been met. Each input is connected to one and exactly one member of the outputs, right? We didn't say sometimes one is 3 and sometimes one is 0. No, that's ridiculous. 1 is always 3. So, let's look at the pictures John draws and learn this new way he has of asking the question. 84.5, and I'm just going to draw them all for you. They're in your book. See, what he's doing is now he's just showing us the inputs and the outputs, the domain and the range. We're not talking about the function itself. We're just looking at this mapping relationship. So we don't know what the function is. John just draws this much for us. So what he's saying, and he tells us this is the domain, and this is the range, which is exactly what we would expect. Okay, so what he's saying is that for every member of the inputs in the domain, they connect across, and they each have a matching image in the outputs. That is exactly what a function is. And John's asking us, does the diagram designate a function? Yes, because each input has one and only one corresponding output. So this is a yes. This is a function. Okay? Now, some students get frustrated because they're like, but how? How does 4 connect to 7 and 5 connect to 2 and 6 connect to 14? How? What's the equation that would make that work? We don't care about that right now. We don't care about the function itself. We're just looking at the domain and the range to see if they're behaving like numbers in a function should behave. That's all we care about. We don't care about how we calculate these pairs. We're just saying, okay, somehow somebody got an equation to make this work. Does it look right to us? .6. I thought it was 5. Here comes another one. Now John's getting a little crazy because he's using letters. Oh my gosh, John. It seems harder, but here's the thing. We don't really care how these things get matched or imaged or connected together. We just care that they do it in the proper way. That's all John's asking. He says that Y is connected to P. Okay, that looks good. And he says that A is connected to X. Perfect. Lovely. M is a little more complicated. He's got an arrow going up here, and he's got one going here. So what he's saying is that Y always connects to P, A always connects to X, M sometimes connects to X, and sometimes connects to 5. No, 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 no. That is not going to work. M can only have one image. So this is not a function. And it's all because of this problem right here. M has 2 images, is the way we can say that, right? X and 5. That is the deal breaker. Mr. Yuck. Okay, that's why this is not a function. M is trying to have it both ways and it can't. All right, beautiful. Let's go on to the next one. All right, does this diagram designate a function? Again, we're not looking at the function itself, we're just looking at the relationship between the inputs and the outputs, the domain and the range. This is a tricky one. A connects with 5. 4 connects with 5. 7 connects with 11. Again, this is the domain and this is the range, if you'd like. If that makes you feel better, I want to normalize these words in your vocabulary, right? Okay, A always connects with 5, 4 always connects with 5, 7 always connects with 11. That sounds good. Each one of these always connects with one and only one member of the outputs. Does it matter that A and 4 both connect with 5? No, it does not. We don't care if there's repetition here. We only care that each member of each input, I'm going to write this down. Each input connects with or maps to, if you want to use the most mathy terminology, it maps to or it images with one and only one output. And that's what's happening here. The fact that some of these are doubling up is not our problem. So yes, this is a function. We have a bunch of these. We're going up to 12. Now this one looks different and it's kind of confusing. I don't like this kind as much. Again, this is the domain, and this is the range. Inputs and outputs. Every one of these has to map to exactly one over here. Now, this one, we're using a completely different way of describing what's going on here. We're saying that this is the function, this is the equation that we're using to link the inputs to the outputs. This is the same one I used in the beginning, isn't it? X plus 2. And this time, we're not listing specific members of the inputs. We're saying any real number. The rules of this game are that any real number can be plugged into there, which makes sense, right? There's no numbers you couldn't put in there. And then this is just an empty spot. Now, this is confusing because it doesn't seem like we're linking this to this at all. But the function this time serves to describe. The function will tell us how to map each one of these to this. So we say, and it's confusing, I don't like this one at all. We say, yes, this is a valid way to write a function. Because even though we haven't written any outputs, the function itself will help us make that connection or mapping to link them. So if you see something written in this style, take a note, yes, that is a legitimate way to write a function, okay? Seems weird, but it's fine. Okay, now let's try another way of looking at numbers to decide whether or not they're a function. Okay, that was by looking at circle diagrams. That's what I call those last ones. Now we're going to look at ordered pairs. Does either of the sets of ordered pairs shown below designate a function? Okay, and there's an A and a B. Oh, John. Now, imagine that we took 4 and 7 and we wrote them in a set of parentheses with a comma in between them. Imagine we wrote 5 and 2 as another ordered pair and 6 and 14 as another ordered pair. That's what we're doing here. We could, if we wanted, we could write these as a diagram. And we would write 4, whoops, I don't want that arrow there. Here, I'll put it like this. 4 goes to 6. 7 goes to 2. But look, now we're saying, oh look, 4 also goes to 5. Right? So that's a problem. 4 does not map to one and only one output. It's mapping to 2 different outputs. So we know this is not a function. It fails the test. However, without going to all the extra work of drawing that diagram, let me cover it up. Here's how we can look at it. Look at just the inputs or the X values of each of your pairs. See if any repeat. Aha, we do. We have a pair of 4s. Once you notice that the first element repeats, look at the second element. It should be the same. If it's the same, then it would be fine, right? If this said 4 and 6 and 4 and 6, that would be fine. But because our second value is different, that's how we know it's not a function. B. Okay, as we look at this one, again, look at the inputs first, the X values. See if you have any repeats. We do not, so we're done. That's a yes. It's fine. These are all the right answers, though. I have not. I have been dropping the smiley face ball, haven't I? All right. Example 8410 has 4 of these. Which of the following ordered sets, or which of the following sets of ordered pairs are functions? Okay, so we're going to use this rule. First, look at the inputs, see if you have any repeats. If you do repeat, they should have the same output paired with them. If it's a different number, no, failure. Okay, here's A. I'll write them down. And you know what? If you're at all, you don't have to write these down in your homework, but if you're at all confused or overwhelmed by these, Writing them down helps you notice the numbers. This is a 1. The second one starts with a 2. The third one starts with a 3. The fourth one starts with a 4. Okay, so there's no repeat X numbers, so that's automatically a yes. I'm gonna write it here. B. 1, 2. 2, 3. Okay, here comes trouble. There's another 1. I already had a 1. This one's paired with a 2. This one's paired with a 3. Don't even have to finish writing it down. That is not gonna work, people. Right? The inputs match, but they're paired with different outputs. Deal breaker. C. 4, 3, 2, 2. Okay, 4, 2, those are different. Here comes another 4. I hold my breath. Oh, it's paired with 3 again. So that's cool. The inputs match, but the outputs do too. So that makes me comfortable. And then the last one is 3, 3. Okay? The fact that we're getting repetition among the outputs, I don't care at all about that. That doesn't matter to me at all. It's only when we repeat the inputs that we have to double check and make sure the outputs match. This one's good. And the last one, D. One and minus 1. 4. Minus 1. Okay, again, we look at the inputs only and look for any repeats. They're all different, so this should be fine. Now, again, some students will look at all those outputs and go, dude, look at, there's a whole bunch of minus 1s and they're all connected to different numbers, X's. That's fine, we don't care. It's not about repetition in the range, it's about repetition in the domain, right, the X's. If we see repeats there, like these 4s, that's what we care about. That's when we have to take a closer look. All right, so here's the pattern. Yes, B is no, C is yes, D is yes. Yay, we got them all right. Function notation sometimes freaks students out, but I like it because there isn't a lot of calculation. It gives our brains a little break. Does the diagram designate a function? Seven maps to 11. 6 maps to 4, but also to 8. Uh-oh. 6, no, you can't do that. You only get to map to 1 of the range. So, no, you fail. I'm just unhappy with you. Guess what? Finally, last one. Does the diagram designate a function or a relation? Okay, let me tell you what the difference is. Notice that these functions that we've been looking at in these diagrams, they're nutty. I have no idea what equation would let 6 connect to 11, or 7 to 11. It would map those two, but then it would map 6 with 4 or 8. No, it doesn't make any sense. So we're not worrying about that though. We're just looking at the pairs of numbers. And here we have six maps with 4, 7 maps with 11, and 5 is just sitting there. So is this a function? No, because remember, to be a function, every member of the input needs to be mapped with or connected to one and only one member of the outputs. 5 is a loner. And he doesn't have anyone. All right, but John's asking us the second question. Is this something called a relation? What is a relation? It must have a relation is kind of like a broader category than a function. A relation would include situations like this, where 6 has 2 images, not just one. So we know it fails the function test, but at least it's called a relation because 6 does have a buddy. 5 has no one. So 5 is not a relation either. This one, we could say, is it a relation? Yes. Because everybody's got a partner one way or the other, at least one. Poor little 5 is no one, so he doesn't have that. John didn't ask us if this one was a relation. He just introduced that idea down here. But this is a good example of what a relation does look like. So that's why I added that little tidbit. This is the fancy definition of a relation. This is a picture of what a relation looks like or can look like. Okay, guess what? I'm done. Let me just show you in the practice. You're going to multiply some wolves and pigs. Here are some of these diagrams. Then they're asking about domain and range. Remember, domain is inputs, range is outputs. X's and Y's, that's another way of breaking them up. We're going to learn more names later, but domain just means the inputs and range means the outputs. And then here are some where we look at the pairs, which is the same information as this, just arrayed in a different shape. And then you have your problem set. Yay! Okay, we did it. We finished. Thank you. Goodbye.